Welcome to Future Talk. On today's program, we're going to talk about some of the most intriguing areas of high technology, including machine vision, deep learning, and robotics, with a man who's an authority on all of them. Adrian Kaehler is a founder and CEO of a robotics company called Giant.ai. In 1998, he won the Gordon Bell Prize for building the world's highest performance computer. In 2005, he won the DARPA Grand Challenge First Place Award for building the world's first functional autonomous automobile. He wrote a best-selling book on computer vision, and he's a founder of the Silicon Valley Deep Learning Group, an educational, not-for-profit initiative with over 5,000 members dedicated to artificial intelligence and deep learning. Adrian, great to have you on the program today.
It's a pleasure to be here. Thank you for having me.
So let's start with machine vision. How do you get a computer or a robot to see the way a human sees and be able to understand what it's looking at?
We don't know. This is an outstanding problem that folks have been working on for decades. The way that we understand the problem in the beginning is we typically have some kind of imaging device that reads pixels, individual like tiny squares of light, and measures them with some intensity. But that essentially gives the computer an array of numbers that isn't very closely related in any way to what a human being imagines that they see when they look at the world. In the beginning, for many years, people thought in terms of things like the lines that form the edges of things. Try to look at those pixels and find places where those where they're changing rapidly, something like that. You get the kind of silhouettes and try to analyze those in one way or another. Over time, we got more and more sophisticated modes of trying to build our intuition into an image and look at that array of numbers and try to find particular things that we thought would be indicative of what it was we might be looking for, you know, a car or a pedestrian or something like this.
You try to model it after human side, like consider the way a baby learns to differentiate objects. Do you start with that, replicate a human experience, look for areas of similar colors and notice when they move? Because we're not talking about still images alone, we're talking about video, 30 frames a second typically, detecting moving objects and figuring out what they are.
Well, I think in the computer vision community, there's different camps of people that approach computer vision in different ways, mainly because they have different purposes. So, for example, there are people who are essentially neuroscientists who are looking at using the computer as a way to investigate their theories about how computer vision might, how human vision might work. On the other side, there are practical engineers who want a particular kind of result. They want to successfully do a trick. And for them, it's less important to do it exactly the way that they imagine humans might. Often there are many practical shortcuts or approaches that, even though we know humans don't do it that way, we found it to be effective for practical problems.
So do you start with very small patterns basically and learn those small patterns and then integrate them into bigger patterns until you see whole objects? So the computer first recognizes dots, then it recognizes lines, then shapes, and it keeps building on what it's learned before?
This is the intuition probably in both more neurologically oriented and practical problems. We know in the human visual cortex that there are many layers of the cortex, that each one kind of processes data, gives an output, and then the next one looks primarily at the output of the prior layer, right? So in this mode, our intuition tells us that there must be some hierarchical way to build up a detection of things. Having said that, for many years, computer vision researchers really experimented with how this might be done, and often practical engineers had various kind of heuristic tricks for this. But it was only quite recently that we began to get a command of that kind of hierarchical system that was really effective and had any kind of reliability.
I think we've made a lot of progress. For example, with autonomous vehicles, you can drive around in a driverless car. The cameras recognize objects. It can see the traffic. It recognizes street signs. It is aware of its surroundings, 360 degrees, and controls the car appropriately. So that's a lot of progress, isn't it?
Oh yes, definitely. It should also be noted that self-driving cars typically rely on computer vision as well as LiDAR, which is a kind of optical frequency radar that allows the vehicle to find, detailed depth measurements and build a kind of three-dimensional structure around it, separate from and essentially parallel to computer vision. Now in practice, those two things are often merged at different layers in the software stack that operates the car. But in many cases, finding things is often done first by the LiDAR system because a three-dimensional structure is often easier to decompose. And then computer vision is used to determine what a particular component of the scene actually is.
Now we have some images that illustrate some of the things we're discussing about machine vision. Can we see that first image, please? So what are we looking at in this picture?
Okay, this is a picture just to help us understand what a common computer vision problem might look like. One of the classic problems in computer vision is classification. Given an image, we ask ourselves, what is this an image of? And if you take a look at this image, you quickly, and all the little component cells in it, you quickly get an idea how varied something might be. Look at all the images that are labeled as elephant. They all look to us very similar in the sense that we quickly recognize that they're all elephants. But if you look at them in sort of the way the computer sees them, some are basically green and some are basically brown and some are really focused on the head of the elephant and others show it in profile and so on. Or if you look at the boats or the pumpkins, they're really all quite different from each other at the pixel level. So this image is intended to convey a little bit about what are the real challenges in building a computer vision system.
So does the computer build a database so every object that it identifies, it stores that away, and when it looks at something new, it compares that object to what it has stored in its database to see if it matches anything?
This is kind of the traditional way that people imagine this problem would be solved. In the prior, let's say, 2 decades, there was some ideas of template matching or some kind of database of structures that you could relate things to. The more modern systems, I guess they do that in a more subtle way, but there isn't an explicit database. More modern systems are really based on analyzing this kind of hierarchical representation and layer by layer, getting closer and closer to the ability to decide between the classes that the system has been trained on.
Now, what do we expect to be able to do in the relatively near future with this type of vision? Will it be able to have visual capabilities that humans don't have?
Yes, at least there will be some things. What we've seen is, after some 20 years of struggling with this problem and trying to build these hierarchies of representation that our intuition told us would work, and also a general belief that systems that behaved in a manner that was at least analogous mathematically to how we imagine that human neurons behave, what we call artificial neural networks, a long period went on where both of these intuitions were strong, but the actual technical ability to realize them as algorithms was not mature yet. In about 2012, for computer vision, there was a really significant set of breakthroughs that began the era that we now associate with the technology called deep learning. And deep learning is really just the final beginning to succeed of this intuitions that we've had, that we could represent things as layered hierarchies, and each layer would be sort of dependent only on the input layer and a little more subtle or abstract in what it was that it was detecting, ultimately to some final layer that sorted things into categories like, elephants and pumpkins.
Okay. Well, let's look at the next graphic here and see what that is. So what is this showing us?
Well, this image is intended to convey this intuition and how we thought we would approach computational neural networks, and also why it didn't work until recently. So if you look at the top image in the 80s, this is to help us understand why were we not successful. For example, Thinking Machines Corporation was built in the 80s with essentially the goal of solving the problem we now call deep learning. They built very powerful supercomputers, and they analyzed artificial neural networks and tried to train them and build systems that could do, solve vision problems, among many others. But they were not successful, and the reason was because at that time no one really realized that the internet itself was a necessary precursor to successful neural networks. And the reason for that is because the neural networks require an enormous amount of data. So if you imagine in the 80s, if you wanted to build a visual database that had, let's say, lots of cats and lots of dogs and lots of trucks, something like this, then when you actually go to do that, where do you get those images? You get your camera out, you call your friends on the phone, maybe leave a message on the answering machine, hey, can I come by and photograph your cat, right? Drive through Photomat or whatever. It's a very painful process to build up a database of any size. So typical databases might have a few dozen categories and at best maybe 100 images in a particular category, right? And then when we tried to train neural network-like systems with data of that kind, it just didn't work. We didn't really know at the time why. But in hindsight, we realized that that was just nowhere near the amount of data that was required, and those networks were nowhere near as complex as was required. So if you look at the modern era, which the lower part of the graphic is meant to convey, now you go to the internet if you Google search for cat images, you can get 1 million images in as many microseconds. And that ability to create very large databases was actually what gave us the ability to successfully train these kind of neural style networks for the very first time.
So you're saying that if you could crunch enough data, you could solve all these problems. It's basically dependent on being able to manage enough information.
Yes, but to put it in context, you mentioned in the beginning of the introduction that my team at Columbia University built a teraflop supercomputer. In those days, a teraflop was the biggest thing you could imagine. It filled a room and fans everywhere and so on. That's typical of what you would find in a modern high-end graphics card that's used to train deep networks today. The compute power wasn't actually out of reach even in the mid-90s. I mean, obviously it was bigger and more expensive, but it wasn't out of reach. The thing that was out of reach was the data, the actual input data. You and me, by the time we're old enough to know a cat from a dog, we've actually experienced millions, perhaps billions of frames of cat and dog images with our eyes. We didn't really understand that in order to train these networks to do those tasks, we would need data volumes on that scale.
I think we have one more image. Can we see that last image, please?
This image is a kind of schematic representation of how these networks work. I won't probably go into all of the details, but essentially it's capturing this idea that the image is analyzed by these layered modules. Maybe the first one marked C1 is simply taking input in. The next one marked C2 is looking at that image and looking for patterns, and then C3 is looking for patterns in those patterns, and so on. When it gets out to the end, these network layers labeled FC6, FC7, and so on, they, rather than kind of scanning the whole of the layer, they're combining what's been found on the input layers. But in essence, this is kind of a topology for an artificial neural network. To understand a little better what that achieves, look at the images on the bottom. You see the image of a woman's face. But what happens is, as it's trained on many faces or many images, the network learns that in the beginning, let's say the C2 layer, it should start looking for these kind of bright edges and line fragments. What it does with that is that layers deeper in, it then searches for patterns in those line fragments that have a particular structure. Like you might notice that some of these little bits marked combinations of edges are bits of mouths or bits of ears or things that might be face parts. And then at the very end, those nodes are searching for what are here marked object models, which basically in this case look like entire faces, but understand that those faces have been learned as particular kinds of assemblies of eyes and noses and such, and the eyes and noses are particular assemblies of edges, and that's how the whole pipeline works, from image all the way through to a recognition decision about what it's seeing.
I know computers are getting better at recognizing things because those little CAPTCHA things keep getting more complicated. You have to explain what's in the picture one way or another. It used to be simple text with maybe a funny font, and now sometimes it's hard for the person to tell what they're looking at. And those, like, you have to check that box to verify that you're not a robot yourself, and they show you a picture. And those CAPTCHA images are getting pretty complex. Find all the pictures that have a boat in them or something like that.
That's right. Well, actually, in many cases, the CAPTCHA task is one that the computer only partially knows how to do, and you're being asked to do the part the computer doesn't know how to do. Believe it or not, in many cases, you're contributing to the construction of a data set that will train an algorithm as much as you're being tested. You're also the teacher. Now,
what are some of the possible uses of computer vision? I would imagine that it wouldn't have to be limited to the visible light range. Presumably, robots could see in infrared and ultraviolet, which might add additional useful capabilities?
Certainly. There's many ways in which computer vision can, on one hand, we're spending a lot of effort learning how to do things that humans can do, and we haven't been 100% successful there. But there's a lot of interesting things to see outside of human capability as well. Humans are limited we scan the area with our eyes, and only a tiny bit of our vision has very high resolution. If I can have a very high resolution computer camera that essentially sees the entire scene in high resolution, and if I have the compute power to analyze it, I can find anomalies and subtle things that a person might well miss. You mentioned what's people call extended optical or infrared. This EOIR type cameras, you may be able to see, for example, in the infrared, and the infrared may contain information that pertains to a particular problem. For example, it's very heavily studied problem in how to use extended optical and infrared imagery to look at crops, for example, and determine the vitality of the crops or whether they have disease and things like this. In fact, that concept can be taken a step farther into what we call hyperspectral imaging, where humans see red, green, and blue. Many kinds of birds and other animals can see many more colors than just human beings, just the three that human beings can see. And for example, if we have an image where we have many spectral segments that we can see, many subtle color variations, then we can use these kind of machine learning techniques to learn to find very subtle things that are invisible to the human eye, but in the hyperspectral domain, and often extending into the infrared or ultraviolet gives you very important insights in that case as well.
Let's talk a little bit about deep learning. Is this basically an attempt to mimic the human nervous system, where you acquire input and then you organize it and then you remember what you saw, and each thing you learn is a building block to learn the next thing? Are we trying to mimic that kind of human performance?
I think that deep learning is our contemporary term for things that artificial neural networks do that have been successful recently that were not successful in the past. So it's a bit of a jargon term that means neural networks that actually work. But neural networks of this kind come from really two different thought streams, and I kind of alluded to this earlier. There's been a community all along that was very fundamentally interested in the biological problem: how do humans think, or how do animals think, or neural networks operate in nature, and then use the computer as a way to try to study that. And then another group that's really just trying to get something done, but they consider the biological neural networks perhaps a useful guide as to how that might happen. In recent times, there have come to be a set of computational models for a neural network that, at least we believe, capture a lot of the salient ideas that drive animal neural networks, but are simple enough to simulate on a computer. And so when we talk about deep learning, we're really saying, how do I create a network of, if you like, neurons, but they're sort of neuron models, and train them to behave in a way, which is to say, learn the neural weighting coefficients to make them behave in a way that is at least similar to what we expect of humans or animals.
Is this still all about processing information, seeing something, recognizing it, or do neural networks create the potential of making decisions, maybe making judgments, maybe moral judgments, or does it have to be programmed to seek a certain objective?
Well, I think the big difference between deep neural networks and in general the modern neural network and AI era and the way we've approached computers in the past is we don't really program them. We show them examples of things, and by way of those examples, they learn to generalize. So if you think about the picture we looked at earlier with the elephants and so on, if it sees a lot of elephants and it sees a lot of dogs, we expect that if we give it a novel image of a dog, it would successfully agree that that was a dog, right? In this kind of simple system, there's a classification process, and there are labeled images that are being given to it. It might be millions of such images, right? And then some generalization kind of emerges. But notice that in this case, no one is literally programming it in the way that we normally think of programming in C++ or something like that. The network already is structured, and it's presented with data, and the same network presented with different data will learn to do different things. And we don't program it as much as we train it. So it's sort of more like a dog and less like a Commodore 64.
So you can't figure out how it arrived at its decision necessarily, just like you can't figure out how a human arrived at his decision about something. It just sort of happened.
That's right, and this is a very serious topic in the world of deep learning, in the deep learning community, because increasingly we would like to apply these algorithms to problems that are very significant, like, for example, vehicle navigation. Well, if the vehicle does something wrong and it suddenly decides to crash into a lamppost, we might wonder, why did it do that? And the kind of introspection which is possible in procedural programming of the traditional kind does not have any direct analog in the neural network environment. And so even by studying careful logs of the data that caused that, at the time of the crash, it may still be at best a very subjective activity for a bunch of scientists to say why they think it happened, and to address the question of how they would make sure it didn't happen again. Reliability and provability are very important frontier topics in the deep learning community.
Let's talk a little bit about robots, because we have machine vision and we have deep learning, and we combine these in robots which can be movable, they can walk, they have arms, they can grasp things. So a robot can see, and you give it a goal to accomplish. What are the capabilities of robots nowadays? What can they do? Can they actually, can you give it a general instruction like, okay, walk out of this room, so it has to figure out where the door is, figure out how to open the door. But just with the initial instruction, which is sort of abstract, it can figure out all the steps to accomplish that.
Yes, well, there's several, when you think about the problems that, when you encounter a person, you ask them to do something, you often don't decompose it into all of its difficult pieces. With a robot, you quickly discover how many implicit things are in the problem. If you tell the robot, get me a cup of coffee, there's a lot of questions. Is there coffee in this building? Are you asking it to drive a car to the local coffee shop? And then deconstructing that all the way down to the very minute tasks of how the robot will say if it walks, how it will place its foot, how it will shift its weight to not fall over, this kind of thing. Some of these problems are actually things that have been addressed for many years in the robotics community, and the solutions that we had then are the solutions we use now. There are other parts of this problem which technologies like deep learning have played a significant role in moving them forward in a quite qualitative shift from maybe not working towards working.
Do you think we'll get to the point where we'll all have cheap household robots that act as your butler or your valet or your cook or your house cleaner, and most people will have one of these and it'll just perform all the routine chores in your house? You give it an instruction, cook me a pot roast tonight, and it figures out how to do it.
I think that result is essentially inevitable. I think the robotics community has very different feelings depending on who you ask about how hard that problem is and when that might happen. But speaking in general terms, there's no doubt that many, many people and many brilliant academic researchers and very focused startup companies, as well as larger companies with similar interests, are all kind of making their way to that vision in one manner or another. And I think there's a pretty strong feeling that there's no fundamental reason why that won't happen, but there are still a lot of unknowns between here and there.
Are there any downsides to robot, for example, taking over people's job? Robots can do many jobs faster and better and cheaper than any human.
There are probably downsides. I don't think that the taking away of jobs is the one that we should all really worry about. This is a bit subtle point, but at the time, right now we're building robots that are capable of doing all kinds of things, but if you look at the demographics of our population, the older retirement age population is becoming ever larger relative to the working age population. That's a relatively significant problem in the United States, but it is a very severe problem in countries like Japan and Germany. And in the case of China, it's even more complex because they had a one-child policy for some time. And that one-child policy, in very short order, will cause that particular, what's called a demographic, like a dependency ratio in the demographics community to go to sort of an all-time low. So the number of working age people available to care for older people and children is going to be lower in the future than it's ever been. And so in that case, I would say we really need these robots to be able to care for the part of the human race that is not able to work as easily and to produce the goods and services that those people will need.
Do you think we might come to rely too heavily on decision-making by machines? Should we depend on machines to make our foreign policy decisions, tell us when we should go to war or when we should seek peace? Or are there some things that humans will always be better at than machines?
Well, the very contemporary topic in the news is the degree to which such algorithms played a role in, for example, the last United States election. there is ample opportunity to apply deep learning and artificial intelligence technologies to cyber warfare and other kinds of aggressive or defensive military activities. There's also there is an increasing reliance on analytic systems to give us insights into large amounts of data. I don't know that people are rushing to have AI algorithms make critical decisions in themselves to decide whether or not to go to war with some country. But at the same time, there's a very real problem that algorithms whose behavior is not fully understood can produce advice that is difficult to question, right? So, if the algorithm says there's a large number of troops building up on the border between country A and country B, what you do about that may still be your human decision, but it may be very hard to question whether or not that's really true in the first place. That's part of why this issue of introspection is very important in networks.
Now, some people feel that robotics raises the question of what humans are actually good for. If robots can do most things as good as humans, then we might say, well, why do we need humans? Or maybe robots are more valuable. Do you think that putting robots on somewhat of a par with humans maybe will tend to cheapen the value of human life, make human life less important or more expendable?
I suppose one can imagine a kind of robot that has a artificial intelligence that looks human-like, but I would generally categorize that for the moment as science fiction. I wouldn't worry so much about how we share the planet with our sentient robot friends. It's a fascinating question, but it's not one I think that's going to come up in any of our lifetimes. I think the more interesting question is how human life has been cheapened by a lack of robots. How many people are essentially spending their life, they get up every day, they go to work in some environment and they do some very monotonous task. In effect, we're paying them to be robots. So I actually see it the other way around. I think that having robots to do many of the things that we rely on other human beings to do that are really not very profound tasks, they're not things that we respect or value. Having the robots to do those tasks actually frees the human beings, in my opinion, to be more human.
I think we're going to have to leave it at that because we are out of time. I'd like to thank my guest, Adrian Kaehler. Thank you for watching. Visit our website, www.futuretalk.net. For Future Talk, I'm Marty Wasserman, and we'll see you next time.